Hello, and welcome to your ultimate guide for the D429 OA, Introduction to AI for Computer Scientists course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your D429 OA exam with total confidence. In this video, we'll cover Agent Core, P's framework, environment dimensions, agent architecture, learning components. With over 100 plus success stories, we have proven our videos will help you pass your exam on the first attempt. And remember, our website offers free exam guides and practice questions to help you ace your D429 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's get started.
So what exactly is an agent? An agent is anything that can be viewed as perceiving its environment through sensors and acting on it through actuators. Notice that phrase, anything viewed as. Being an agent is a point of view we adopt, not a special object. Even a human or thermostat fits. Consider the two channels connecting an agent to its world. Sensors are the components through which an agent receives information, and a camera is the classic example in artificial intelligence. Actuators are the components through which it acts, like a motor, wheel, gripper, or speaker. Sensors bring information in, actuators push action out. Now, here is a distinction examiners love. A percept is what the agent senses at a single instant, one snapshot. A percept sequence is the entire ordered history of everything it has ever perceived, the whole film. Why does this matter? Because the right action can depend on something seen minutes ago. This next pair is the most confused idea in the module. The agent function is the abstract mathematical mapping from every possible percept sequence to an action. It is the what, a specification on paper. The agent program is the code that computes those actions. The program implements the function. Consider the famous vacuum cleaner world. Picture two squares, A and B, each clean or dirty with the agent in one. It senses its square and whether that square is dirty. Its actions are suck, move left, and move right. Because this world is tiny, we can write its full agent function as a table. Not every agent has a body. A software agent is a program acting for a user inside a software environment, perceiving through inputs like files and network data, and acting through outputs like commands. A smart agent adds autonomy and learning, and an AI agent uses artificial intelligence techniques to act. They share one perceive, decide, act skeleton. So how do we judge whether an agent is good? With a performance measure, an objective scorecard set by the designer. Here is the golden rule. We measure performance by the state of the environment, not by the agent's own opinion. A clean floor is what counts, never the vacuum's belief that it succeeded. Why insist on this? Because if an agent grades itself, it could feel successful while accomplishing nothing, or even while making a mess. Tying success to real environment states gives an honest standard the agent cannot game. We also judge over the long run, and since the world is uncertain, we ask for maximum expected performance. On your OA exam, this first concept appears everywhere. You will get a scenario and be asked to identify the sensor, the actuator, the percept, or the performance measure. Watch out for the classic trap of confusing the agent function with the agent program. Remember, the function is the math, the program is the machine. Here is a memory trick to lock this in. Picture the agent function as a restaurant menu, listing exactly which dish arrives for every order a customer could place. The agent program is the kitchen and recipes that make each dish. Two different kitchens can serve the identical menu. That keeps the mapping and the code separate. What we just covered is exactly the type of material in our free practice question bank. These are not just basic recall questions. They are designed to test your deep understanding, just like the real OA exam will. So head to that link in the description whenever you feel ready to practice. Now, what makes an agent good? The answer is rationality. A rational agent is one that for each possible Percept sequence selects the action expected to maximize its performance measure, given the evidence it has perceived and its built-in knowledge. In plain words, it does the best it can with what it knows. Whether an action is rational depends on 4 things together. First, the performance measure defining success. Second, the agent's prior knowledge of the environment. Third, the actions it can perform. And fourth, the percept sequence so far. Change anyone and the rational choice can flip. Rationality belongs to the situation, not the action alone. Here is the part most students get wrong. Rational does not mean perfect, and it does not mean all-knowing. Picture crossing an empty street to greet a friend when a cargo door falls from a passing plane and flattens you. Were you irrational? Not at all. We judge by what was knowable, never by hindsight. Rationality also demands action, not just thinking. Information gathering means acting in order to perceive better, like turning your head to look both ways before crossing a road. Exploration is its cousin in unfamiliar settings where the agent must try things to learn how the world works. A rational agent is never passive before ignorance. This leads to autonomy. Autonomy is the degree to which an agent relies on its own percepts and learning rather than knowledge its designer built in. Why does this matter? Because no designer anticipates everything. An agent that only follows fixed rules eventually acts irrationally when reality differs. So a rational agent learns and grows more autonomous. Now we shift from judging agents to designing them, starting with P's. Before building any agent, your first step is to specify its task environment as fully as possible. P stands for performance measure, environment, actuators, and sensors. Skip this step and you have no definition of success, no actions, and no list of percepts. Let us work through the hardest example, an automated taxi. Its performance measure includes safe, fast, legal, and comfortable trips. Its environment is roads, vehicles, pedestrians, and weather. Its actuators are steering, accelerator, brake, and horn. Its sensors are cameras, LiDAR, radar, and GPS. Notice how the goals conflict since fast pulls against safe. Software agents have P's descriptions too, and this trips people up. Take a medical diagnosis system. Its sensors are the keyboard entries of symptoms and the lab results it reads. Its actuators are the screen displays of questions and recommendations. The lesson is that for a software agent, sensors and actuators are simply input and output channels. For the exam, memorize the 4 P's letters and what each means, because questions often ask you to fill them in or spot a mistake, like listing a sensor where an actuator belongs. Also remember rationality versus perfection. An agent can act rationally and still get an unlucky result. A good decision is not a good outcome. To remember P's, say the word P's like the vegetable and unpack it as performance, environment, actuators, sensors in that order. And to capture rationality, hold this phrase: do the right thing, given what you know. Not the perfect thing, not the lucky thing, but the best expected choice with the evidence available. I know we are covering a lot, and you might wonder how to practice applying all of it. That is exactly why I put together those free practice questions. They walk you through problems that combine several concepts at once, which is precisely how the real exam tests you. Give them a try soon. Now we reach one of the richest topics, the properties of task environments. Artificial intelligence classifies every world along 7 independent dimensions. Think of each as a question you ask about the world, and the answers together tell you how hard the problem is. Because they are independent, a world can be observable yet unpredictable. The first dimension is observability. A fully observable world lets the agent's sensors see everything relevant, like a chess program seeing the whole board. A partially observable world hides part of the relevant state, like a taxi that cannot see around a corner. The consequence is memory. Partial observability forces the agent to remember and infer. The second dimension asks whether the agent is alone or shares the world. In a single agent world, like a crossword solver, the surroundings are passive. In a multi-agent world, others pursue their own goals. If those goals conflict, it is competitive, like chess. If they align, it is cooperative, like delivery robots avoiding collisions together. The third dimension is predictability. A deterministic world means the same action in the same state always gives the same result, like writing a letter into a crossword. Uncertainty has 2 flavors. Non-deterministic means several outcomes with no probabilities. Stochastic means outcomes with quantified probabilities, like taxi driving, which lets the agent choose the best average action. The fourth dimension asks whether decisions are linked over time. In an episodic world, each decision stands alone, like inspecting parts on a line where judging one has no bearing on the next. In a sequential world, today's action shapes tomorrow's options, like chess, where a careless move can lose the game later. Sequential worlds force look ahead. The fifth dimension asks whether the world changes while the agent thinks. A static world waits politely, like a crossword that never rearranges itself. A dynamic world keeps moving while you deliberate, like traffic, so you must decide quickly. A semi-dynamic world is the middle case, like chess with a clock, where your time keeps ticking. The sixth dimension is granularity. A discrete world has a countable number of distinct states, percepts, and actions, like chess with its finite list of legal moves. A continuous world varies smoothly over real valued ranges, like a car whose position and speed change without distinct steps. Be careful. Discrete has nothing to do with size. The seventh dimension is whether the world is known or unknown. In a known world, the agent is told the rules in advance, so it knows what its actions do, like chess with its rulebook. In an unknown world, it must learn by experimenting, like a new game with no manual. Known means plan, unknown means learn first. Here is the anchor tying all 7 together. When in doubt, ask, is this more like chess or like driving? Chess is fully observable, deterministic, discrete, and known, sitting on the easy end. Driving is partially observable, stochastic, dynamic, continuous, and multi-agent, stacking almost every hard property at once. That is why self-driving is so difficult. On the exam, you will get a scenario and be asked to classify it along these dimensions. So practice mapping examples to definitions both ways. 2 traps catch students constantly. First, known versus unknown is not the same as observable versus partially observable. Second, discrete is about countability, not size. Keep those pairs straight. How can we make 7 dimensions stick? Lean on the chess versus driving contrast, since those 2 sit at opposite ends of almost every axis. Chess is the tidy, predictable world, and driving is the messy, unpredictable one. If you can explain why they differ on each dimension, you genuinely understand all 7 properties. If some properties feel challenging right now, do not worry. That is completely normal, and it is exactly why I built that practice question bank. Working through real classification problems is the fastest way to make these distinctions automatic. The questions are free, the link is in the description, and your future self will thank you. Now, let us open the box and see how agents work inside, giving us 5 agent types. We could imagine storing the whole agent function as a giant table, but for any real task, it would need more entries than there are atoms in the universe. So instead, we write a compact program that computes actions. The simplest type is the simple reflex agent. It ignores history and acts only on the current percept, using condition action rules of the form, if this condition, then that action. A thermostat is the classic example. If the temperature is below the set point, turn on the heat. It is rational when the world is fully observable. But what if the agent cannot see everything? That is where the model-based reflex agent comes in. It keeps an internal state, a memory of the world, updated using a model of how the world evolves and how percepts relate to reality. A self-driving car uses this to track a vehicle in its blind spot. The third type adds what the reflex agents lack, a goal. A goal-based agent has an explicit goal and uses search and planning to reach it. It looks ahead, asking what will happen if I take this action. Tell a car to reach the airport, and it plans a route, replanning if a road closes. The fourth type is the utility-based agent. A plain goal is all or nothing, but real life needs trade-offs. A utility function maps each state to a number measuring how desirable it is. So the agent can compare states that all reach the goal and balance aims like speed, safety, and comfort, weighing good against likely. Let me make this vivid with a delivery drone choosing between 2 routes. The fast route over the lake usually arrives quickly, but sometimes crashes in the water, a costly disaster. The slow route always arrives safely. Although the fast route looks better at best, its risk drags its average down. So the rational agent picks safe. The fifth type is the learning agent, special because it can sit on top of any of the other 4 and make them better over time. Rather than staying frozen at its initial programming, it improves from experience. Think of a self-driving car that learns when to brake by watching a human driver, refining its rule until smooth. These 5 form a ladder where each type contains the previous one and adds exactly 1 new power: memory, then looking ahead, then trade-offs, then self-improvement. The rule guiding utility choice has a name worth knowing: the principle of maximum expected utility, picking the action with the best average outcome. More capable is not always better. For the exam, watch for the word only. If a question says the agent acts based only on the current percept and fixed rules, that is the signature of a simple reflex agent. The moment memory, goals, or utility appear, it is more advanced. Remember that a real self-driving car blends all 5 at once. To remember the ladder, picture climbing 5 rungs. Reflex reacts, model remembers, goal plans, utility weighs, learning improves. Each verb captures the 1 new ability that rung adds. Say those 5 word pairs out loud a few times and the whole progression locks into memory, ready for any question, asking you to name a type. Remember that mastering these architectures takes practice. The free practice questions are designed to help you take what you are learning here and turn it into exam-ready skills. They mirror the real question formats. So when you sit the actual exam, nothing feels unfamiliar. Find them through the link below whenever you're ready. Now let us go deeper into learning agents, the most important idea in modern artificial intelligence. A learning agent has 4 components working together: the performance element, which selects actions; the learning element, which makes improvements; the critic, which judges behavior; and the problem generator, which suggests exploration. Performance acts, critic judges, learning improves, generator explores. Let us take each component in turn. The performance element is the working agent, the part that takes percepts and selects external actions. In fact, it is exactly the reflex model-based, goal-based, or utility-based agent we just studied. Here is the key insight. When we say a learning agent improved, we mean the performance element holds better knowledge. The learning element actually learns. It takes feedback from the critic and modifies the performance element so the agent does better next time. What it can change depends on what that element holds. If those are condition action rules, it refines them. If it is a neural network, it adjusts the weights. This is where self-improvement happens. The critic is the judge. It evaluates the agent's behavior against a fixed performance standard and tells the learning element how well things are going. Why must the standard be fixed and outside the agent's control? Because if the agent could rewrite its own definition of success, it could cheat, deciding that crashing is wonderful. The problem generator is the agent's built-in experimenter. It suggests exploratory actions, sometimes deliberately suboptimal, so the agent meets new and informative situations it would never see by repeating what works. Think of a scientist designing fresh experiments. A taxi that has only driven in sun might be nudged to try light rain. How does the critic speak to the learning element? Through rewards and penalties. A reward is a positive signal that behavior was good. A penalty is a negative signal that it was bad. For a taxi, arriving safely earns a reward, while running a red light earns a penalty. The agent drifts toward reward, away from penalty. This reward and penalty framing connects to reinforcement learning, a branch of machine learning, where an agent learns purely by trying actions and collecting feedback, with no teacher giving the correct answer. The rule it learns for choosing actions is called a policy, and the aim is to improve that policy until it earns high reward. Learning agents face a famous tension, the exploration versus exploitation trade-off. Exploitation means using what you know to grab reward now. Exploration means trying something uncertain to discover a better option. Think of choosing a restaurant. Returning to your favorite is exploitation. Trying a new place is exploration. Explore more early, exploit more as knowledge matures. One more distinction examiners love: training data versus operational data. Training data is the curated, often labeled material used to teach the model before deployment, like past emails labeled spam or not. Operational data is generated live as the system runs, like new messages your filter must classify. Operational experience can feed back into training. For the exam, keep the four components distinct, because the favorite trap is mixing the critic with the learning element. Chant the four verbs. Performance acts, critic judges, learning improves, problem generator explores. And if a question says select external actions, the answer is the performance element, even when the stem mentions learning. As we wrap up, remember that understanding these ideas is just the first step. The real mastery comes from applying them, which is exactly where those free practice questions become invaluable. They are completely free, designed for OA exam success, and waiting at the link in the description. Please do not skip the practice. Let us bring it all together. You now know that an agent perceives through sensors and acts through actuators. Guided by an agent function and judged by a performance measure, you understand rationality as doing the best you can with the evidence you have captured in a piece specification, and you can classify any world along 7 dimensions. You have also climbed the ladder of 5 agent types, from the simple reflex agent reacting to the moment, through model-based, goal-based, and utility-based designs, to the learning agent that improves itself. And you have seen its 4 components: the performance element, learning element, critique, and problem generator, realized as reinforcement learning. That is a powerful picture. How do these pieces fit together? Beautifully. The environment properties tell you how hard a task is, and that difficulty tells you which agent architecture you need. A simple, fully observable world suits a reflex agent, while a messy, uncertain one demands utility and learning. Once you see that link, the module becomes one coherent story. You have done real work today, and you should feel confident walking into that exam. Here is your next step. Do not forget to grab those free practice questions from the link in the description. With the understanding you built today, plus focus practice, you will be incredibly well prepared. Now go and pass it.